hard to remember back a week, huh? All right, so we talked about the electromagnetic model, starting with the Maxwell equations, coming up with the wave equation and the electric field vector, and then we said, okay, let's switch gears to the scalar model. And in the scalar model, we said, let's restrict ourselves to monochromatic waves. And if we do that, then we said we wanted to, rather than use a real representation for the scalar optical field, we said let's use a complex representation. And so we said that the complex representation of the field is equal to some complex amplitude times e to the j omega t. So what's the name we gave this piece? Complex amplitude. So terminology again. And whether anyone else in the world uses this terminology, at least amongst us as we talk about things, we'll understand what it means. And this complex amplitude, what is it? What information does it have in it?
A times e to the j v of t times e to the j.
It's magnitude of phase.
Okay, so it has a spatially dependent magnitude and a spatially dependent phase. Okay, so for the complex representation, the time dependence is all here in this complex exponential. And so that means the amplitude and phase is in the complex amplitude. So we can always write it out like this. And if we just plug that in, then we have A of r e to the j omega t plus v of r. Okay, so those are all equivalent. All right, and then we said several things that we need to be able to quantify or visualize or specify for any kind of a wave are, first of all, the irradiance, which is watts per square centimeter. And the irradiance is just the magnitude squared of the complex amplitude. And then you look at this expression for the complex amplitude and you say, oh gee, it's just magnitude squared of the actual amplitude. But we're not going to worry about this part so much. We're going to just focus on this because once we have the complex amplitude, we can always get the irradiance by just doing that. Okay, and then the other notion that we set forth was the idea of a wavefront. And we can define a wavefront in one of two ways. We can say, in the case of the complex amplitude only, we can take just this piece and say that that's 2 pi times some integer q. It looks like this is having a problem. And so that gives us a set of static wavefronts associated with the complex amplitude. Or we could take this piece and say omega t plus phi of r is equal to a family of curves or surfaces, or and call that the wavefront. In which case, that's a surface that propagates in time. So either way, we want to think about wavefronts as fine. Okay, so whenever we characterize a wave, then we're always worried about the complex amplitude, and from that we can get the irradiance and the wavefront. And then if we picture the irradiance and the wavefront, we have a good mental idea of what the wave is like. Okay, and then another thing that we noted is that this complex amplitude here is a solution of the Helmholtz equation. So the fact that the complex representation has to be a solution of the wave equation simplifies to the complex amplitude having to be a solution of the Helmholtz equation. Okay, so at that point then, we looked at what a plane wave was, so i.e. an elementary solution of the Helmholtz equation. So for a plane wave then, we've got that the complex amplitude is equal to some constant complex number A times e to the minus j k dot r. So A is complex, so it has a magnitude, it has a phase. And then K, what do we call K?
Wave number.
Or wave vector.
Wave vector. And the magnitude of K, we call that?
Wave number.
Wave number, yes, okay. So we have the wave vector, the wave number. And the wave vector represents what?
Direction we want.
Direction of propagation. So a vector always has two pieces of information, direction and magnitude. So the direction is direction of propagation. Magnitude of this is the wave number. Wave number is 2 pi over the wavelength. Also, we could write it as omega c over n. Nope, that's not right. Omega over c times n. There we go. Okay, and this wavelength is wavelength in free space divided by refractive index of the medium that we're propagating. Okay, so if we calculate then the irradiance, it's just the magnitude squared of this thing, and so it's just the magnitude squared of that complex constant A. And a wavefront then is omega t minus k dot r is equal to 2 pi times q, q being an integer, and that's just a family of planes, and those planes are separated by a wavelength. So any questions about this stuff? Are we good?
Excuse me. I just don't understand why irradiance is important for us. I mean, we calculated for all the solutions.
So, if we imagine a physical scenario where, say, we have some sort of a transmitter, whether it's a laser or whether it's an antenna, whatever, then the propagating wave that we send out from that transmitter, we can characterize it in terms of its irradiance. And then if we have a detector, the detector will have a finite aperture. And if we know what the irradiance is instant on the aperture, that's pretty trivial to calculate how much power the detector receives.
So then what about the gain? Gain is not enough for us.
So gain is used in the RF world, but not really in the optics world. Yeah, there's no real notion of gain. I mean, you could take that same concept and apply it in the optics world, but it's just not useful. Because optical transmitters tend to be very directional. And so you just don't really worry about it. So instead, you just calculate the irradiance, and then once you have the irradiance, then you have everything you need to easily calculate power into the detector.
Cool, thank you.
Yeah, good question. Okay, then we talked about spherical waves. And in the case of a spherical wave, the complex amplitude is some complex constant A divided by R times e to the minus j k times r, where this k is not the wave vector, it's the wave number. And r is just distance from the source that is generating the spherical wave. Okay, and then we talked about paraboloidal waves, but I don't want to go through it. At that point then, we said, okay, we've been dealing with monochromatic waves. What happens if we have a polychromatic wave? And so for a polychromatic wave, we said, gee, let's deal with a complex representation. And to get there, first of all, we'll recognize that the real polychromatic optical field, we can always consider it to be sort of a sum or integral of u sub nu of r e to the j 2 pi nu t d mu. And we recognize this as simply the complex representation of a monochromatic wave at some frequency nu. And so in other words, this polychromatic wave is just the sum over a bunch of monochromatic waves. I mean, the integral is essentially a sum. Okay, so that means we can always find the complex amplitudes of the monochromatic components of the polychromatic wave as just the inverse Fourier transform of the real representation of that polychromatic wave. Okay, so thinking about things in those terms then, we can write down the complex representation of the polychromatic wave as 2 times the integral from 0 to infinity of these monochromatic complex representations of waves. So e to the j 2 pi t d mu.
Should the line above that also be d mu?
No, this is the forward Fourier transform. This is the inverse Fourier transform. Yeah. So in other words, over here there's no spatial dependence, but there's a frequency. Okay. So if we write the complex representation of the polychromatic wave in that manner, then the real representation is just the real part of that complex representation, which is what we would hope. Okay. And then we said, hey, what if we have a quasi-monochromatic wave, which means that the range of frequencies that we have here is really small compared to a center frequency. Then in that case, we can write the irradiance as just magnitude squared of this complex representation, which is analogous to this form for a monochromatic wave. But you notice there's an extra time variable there, just because for a quasi-monochromatic wave, well, for a monochromatic wave, by definition, it never changes in time. For a quasi-monochromatic wave, it could slowly change in time. So we put the explicit time dependence in here just to remind ourselves of that fact. And then we said, hey, we need to understand the notion of a power spectral density. And that is just plotting, let's call it S nu. Plotting is a function of nu, meaning frequency, what the distribution of the power is. And if it's quasi-monochromatic, then it's going to look something like this, where there's the central frequency, and there's delta nu. And then this parameter here, the power spectral density, has units of watts per centimeter squared per hertz. So we take the power spectral density and multiply it by some differential spectral width, then that is irradiance over that small interval of frequencies. Yeah.
Sorry, the units for radians is watts per centimeters per hertz?
No, sorry, this right here, the power spectral density.
Oh, I see.
Yeah. Okay. So the reason why we're saying something about power spectral density is that in real life, there is no such thing as a monochromatic source. Every source has some bandwidth, however small it may be. Therefore, in real life, the best we can do is quasi-monochromatic. And then conceptually, we can let that go in the limit to monochromatic, in which case we have all this stuff. And very often, if we're narrow band enough, then we don't have to worry about the details of that tiny spectral width, and we can just do this stuff. But what we're going to see next lecture is that this is absolutely crucial when we worry about coherence. And so that's why we have to set the stage for that by just understanding what we mean by power spectral density. And then when we get to interference, the only way we can have two or more beams interfere is if they are coherent. Therefore, we need to understand the effect of that on coherence in order to understand whether we can even get interference in the first place. I saw my peripheral vision,
No.
my hand went up, okay.
Nope, just an itchy face.
Okay. All right. So this is about where we got to last time. And now what we want to do is move forward. And in moving forward, what we want to do is jump back to the electromagnetic model. So we just took this excursion through the scalar model. And the reason why we did is because things are simpler in the scalar model. But now we need to go back to the electromagnetic model and essentially do the same thing, except for electromagnetic waves, and see how they differ from scalar waves. And at the end of all this, one of the things we want to do is say what is specifically the relationship between a scalar wave and electromagnetic wave. And we'll come up with a relationship for that. Okay, so if we go back to the electromagnetic model, we want to specify elementary solutions to the relevant controlling equations so that we get back to this kind of stuff except in the electromagnetic model. And to do that, first of all, we need to specify that we want to consider monochromatic waves. Why? Because they're easier. And if we understand monochromatic waves, it's easy to understand polychromatic waves because, just like for the scalar case, a polychromatic wave is just going to be a sum of monochromatic waves. So if we get the monochromatic waves down, then we pretty much get polychromatic waves for free. Okay, so with monochromatic waves then, the electric field vector we can write in such a way that all the time dependence is in a complex exponential. But just like over here, as soon as we did monochromatic waves, we jumped to a complex representation. We're going to do the same here because it just makes everything so much easier. So we're going to write this real electric field as the real part of something that's only spatial dependent times e to the j omega t. So in other words, all the time dependence is here in that complex exponential, and then by definition, it is monochromatic. So if we look at this over here and compare it to this over here, what's the difference? complex amplitude is different, and it's different how? It's a vector.
Oh, yeah.
Yeah, this is scalar, that's a vector. Okay, now in the literature, there is no name for that. So let's just give it a name between us. Let's call this thing, by analogy with that over there, let's call it the complex amplitude vector. But don't think about that name very hard because it's kind of nonsensical. An amplitude that's a vector, I mean, what is that supposed to mean? But that's just the name we're going to give it. And we're free to do so because there is no agreed upon name for it. So that's our internal code word for it. Okay, so if the electric field is monochromatic, and we can write it as a complex quantity, then the electric displacement, we can do the same thing. And likewise, for the magnetic field, we can do the same thing and write it as a complex amplitude vector times e to the j omega t, etc. for the magnetic flux density, on and on. Okay, and notice they're all of the same frequency. So if we have a monochromatic wave, all of the field quantities are oscillating with the same frequency. Okay, now if we go back to this electric field here, we wrote the real electric field as the real part of this thing. So this thing must be the complex representation of the electric field. So let's write it as E of R of t is equal to this complex amplitude vector times e to the j omega t. And likewise, we can do that for, say, any of the others. Let's just write the magnetic field vector. Okay, and now I've got to introduce you to some notational messiness. So if I write things out this way, if you see an explicit spatial and time dependence, what do you immediately think of as that vector? I mean, what it means? Yeah, it's dependent on both space and time. And so if I see an E with those arguments, that must mean that's the complex representation of the field. And if I need the real representation, no big deal. Just take the real part. Now I've got the real representation. Okay. And then when I look at this thing and just see the spatial dependence, what do I think?
Monochromatic.
Yeah, it must be the complex amplitude vector for a monochromatic electric field. Okay, great. Now, what if I wrote this like that, and I suppress the explicit spatial dependence? Gets shorter. And if we're lazy, then we kind of like doing that. And for better or worse, that's kind of what people do in optics. They take the arguments and they suppress them, making them implicit, and you just have to know that they're there. Isn't that great? I mean, how to be clear, right? So just get used to it. That's just how it is. So it's not worth fighting. You'll lose. So you just roll with it. So very often then we write the complex amplitude vector with an implicit spatial dependence. We don't explicitly write it. Okay, now to make things even funner, often you will see people write the complex representation as just E, suppressing the spatial and time dependence, making it implicit. Now, if we do that, clearly it would be easy to become confused. So my recommendation to you is, don't do that. But if you ever run across it in papers, you can figure it out. If you keep clearly in mind, this business. It's not that hard to figure out. And usually what you do is you smack your forehead and you say, these idiots wrote it in such a stupid way. But you don't ever want to be guilty of that. So just be very clear when you're taking notes, doing problems, thinking about it, doing something in your research where this applies. Just be really clear. And never, ever, ever forget the vector notation. Because these things are vectors. And if you drop that notation, all you'll do is confuse yourself, and you'll absolutely confuse anyone else you try to show your work to. Because it makes no sense. These things are vector quantities. Okay, so we could do the same thing for the electric flux density, the magnetic, or the electric displacement, magnetic flux density, etc., the electric polarization, the current density. It's all going to have the same functional form. Okay, so with that then, each of the spatial components of every single field quantity has to be a solution of the Helmholtz equation. In order for this thing, and therefore that thing, to be a solution of the wave equation. So, that means that the same kind of solutions we get over here for the complex amplitude are the same kind of solutions we get for the individual Cartesian components of the complex amplitude vectors. Now, we need to, if we're going to talk about an electromagnetic plane wave, notice we need to be able to say what the irradiance is, and we need to be able to say what the wavefronts are. The wavefronts, that's going to be easy. It's the same thing. This, we now have to take a half-hour detour to figure this one out. So let's just dive in and do it, bite the bullet. And the result is going to be pretty simple, but it's really important you know how to get there, or where it comes from. Because otherwise you're going to make the same mistakes almost everyone makes in this really basic stuff when you're doing optics. And we don't want you to make those mistakes. Okay, so what that means is we need to go back to energy flow for electromagnetic waves, electromagnetic fields, which means Poynting's theorem. There's no getting around it. And Poynting's theorem is defined in terms of some volume in space. And that volume can have one or more materials in it. And so that volume is bounded by a surface. And each point on the surface, we can define the outward surface normal n hat. So, if we have real electric fields and magnetic fields, we can define the real Poynting vector, and we define that as S of RT is the real electric field crossed into the real magnetic field. So that's the real Poynting vector. We're going to define 3 different Poynting vectors. So this is one of them. Okay. Now, with that definition, we can write down Poynting's theorem.
Sorry, what was the first letter?
S, script S. Yeah. So Poynting's theorem then is defined over this volume. So Poynting's theorem says that the integral over that volume of the real electric field dotted into the real current density, that integral plus the integral over the volume of the real electric field dotted into the partial derivative with respect to time of the real electric displacement plus the real magnetic field dotted into the partial derivative with respect to time of the real magnetic flux density. That whole quantity integrated over the volume plus the integral over the closed surface of the volume of the real Poynting vector dotted into, let's just call it ds for now, that all of that has to be equal to 0. So this is basically conservation of energy. And here, this ds is the surface normal times a differential area. So if I go back to my surface normal here, and I just make a little patch of area dA, then that is what that ds is in that surface integral. Okay, so we've got two volume integrals and a surface integral. Add those things up, it has to be equal to 0. Now, it's important to know what these things mean. So let's call this thing here the first term. I'm just going to say 1. And this thing, second term, and this thing, the third term. Okay, first term, what does it mean? Well, what it's basically saying is that we have, we can write this as the partial derivative of Q with respect to time plus the partial derivative of W with respect to time. That first piece is the energy transferred from the field to the material or materials in the volume. So this term is energy Q that the field is transferring into the volume as heat.
Was that a J?
Which, right here?
Yeah.
Yeah, script J, so that's the current density. Okay, and then the second term is the energy that is going from non-electromagnetic sources in the volume to the field. So if I had, say, I don't know, a PN junction in here, and I was passing current through the PN junction, and some of that current ended up giving off light, meaning giving off an electromagnetic field, then this would be non-zero.
And this is from part 2?
This is all
This
the
is all
first
still
term.
part 1,
Mhm.
okay.
Yeah.
And Q, so Q is heat, it's not charge?
Q is energy.
Okay.
Yeah. And W is energy too, but this is energy in the field. This is energy in the material. And so partial derivative of Q with respect to T is how much energy is the material gaining. And it's gaining it from the field. And partial derivative W with respect to T is how much energy is the field gaining from non-electromagnetic sources within that volume. Okay. Then, the second term is the partial derivative of capital U with respect to t, where capital U has nothing to do with the U on the left-hand board. And instead, this is this term is the rate of change of the energy, the electromagnetic energy stored in the volume V, in the fields that are in the volume V. And we can break that up into an electric field component and a magnetic field component. So this second integral here is all about the rate of change of how much energy we're storing in the electromagnetic field. Okay. And I suppose we could be more, we could write this out a little bit more. The energy stored in the electric field is going to be the integral over the volume of the energy density of the electric field. And the energy stored in the magnetic field, likewise, is just the integral over the volume of the energy density of the magnetic field. And we'll have some expressions for those in a particular case shortly. But the point to understand is just the second term is all about rate of change of energy being stored in the electromagnetic fields.
So there is the rate of change because of energy being transferred from EM to heat and such sort.
Yeah, and we haven't gotten to the third term yet, but something could be happening there in the third term as well. But basically, all these different energy considerations have to balance out, so they sum to zero.
Conservation of energy.
And also, another thing we could point out here that would be useful is that the units of every term are power, watts. So energy per unit time. So every integral has the units of watts. Okay, and so that leaves us with the third term. And the third term is just the rate at which electromagnetic energy leaves the volume through the surface of that volume. Okay. So if we just pay attention to this term for a moment, the integral itself has units of what? Watts. What are the units of ds? Meter squared, centimeter squared. It's area. Okay, so what are the units of the Poynting vector? Watts per area. So, and usually we're doing centimeter squared. Ooh, watts per centimeter squared. What quantity do we know of that has those units? The radians. So our definition for radians is going to come from that third term. But we're not there yet. Because what is this equation good for? What kind of fields?
Repeat that one more time, was the question?
What is this equation good for? What kind of fields? So I just wrote this down, right? Did I say anything about the nature of those fields? It's any general field that's a solution of the Maxwell equations.
We're all right.
Integrated over all of them, yeah. So it could be polychromatic fields, monochromatic fields, whatever. That is always true. Okay, now let's make this specific to the case that we're interested in, namely monochromatic waves, and let's use a complex representation. So if we do that, then this can be simplified, and I'm running out of space, so I'm going to write it right here. And the simplification is that the first term, the integral over that volume, becomes 1/2 E dot J complex conjugate dV. Now, before we go any further, what is E here?
ER and
It's the complex amplitude vector of our complex representation of a monochromatic wave. And so the J, what is it?
Current density.
It's the complex amplitude vector of the current density. Because the current density, we'd write it in the same way. So it's just that complex amplitude vector. Okay. All right. Now the second term becomes minus J omega times integral over the volume of 1/2 the, well, 1/2 of E dot D complex conjugate minus 1/2 of H complex conjugate dot D dV. Okay, now, where did the J omega come from? Yeah, from the partial derivative with respect to time. Because if we take a partial derivative with respect to time, it's just going to pull a J omega down. Okay, so that's where that J omega comes from.
Is that three integral signs or is there a parentheses?
Oh, thank you very much. I'm missing that parentheses. Yeah, thank you. Good catch. Okay, then we have the integral over the surface, and now we're going to write S dot n hat dA, and all of that's equal to 0. And here, S is the complex pointing vector. And so S is equal to 1/2 E cross H complex conjugate. So what is E again? Complex amplitude vector. What's H? Complex amplitude vector. Yeah.
This J in the first term, the 1/2 E, that should also be a J with a line over it, right?
Which one?
Right
The
there,
first one.
to the left, that should have a bar over it, right?
Oh, yes, thank you, perfect. Excellent.
Okay.
Good, thank you very much.
Is that a complex conjugate on the complex function vector for the H thing?
Yes. That funny little thing is a complex conjugate, yes. Okay, so now we have our second type of pointing vector. And now at this point, let's do the following. Let's assume we have the following kind of material. Let's say that it is linear, isotropic, non-dispersive, and of course is a dielectric. What's the one property I didn't specify there? Homogeneous. And since I didn't specify, what does that mean?
Changes over space.
Yeah, so I can have more than one material in here, or the material can be changing continuously, whatever. So if I make those assumptions, then that means that the conductivity is 0, right? If the conductivity is 0, what else is 0? Current density is 0. And we also have that the electric flux density is equal to the permittivity times the electric field. By the way, what V is that? Complex amplitude vector. Same with that. And then if we multiply both sides by e to the j omega t, then we've got this, therefore we've got that, the complex representation. Okay? And we also have that the magnetic flux density is equal to the permittivity times the magnetic field. And specifically, it's going to be the permittivity of free space because a dielectric material is non-magnetic. Okay, so now, if we make that assumption, then this equation we can simplify further. So the first term, notice j is 0, it goes away. So that leaves us with the second term, minus j omega, integral over the volume, and I'll use square brackets here, 1/2, and then d is just epsilon e, right? So that gives me an epsilon magnitude squared of the electric field complex amplitude vector. Are we good with that? So we substituted this for that. Okay, then we have minus 1/2 mu naught, and then we have magnitude squared of b. So our second integral becomes that. Because we just substituted in here, h is equal to b over mu naught, right there. Okay, then we have the integral over the closed surface of the complex Poynting vector dotted into n hat dA is equal to 0. Are we having fun yet? Okay, we're almost there. We're almost to the punchline. Okay, so we have the Poynting theorem equation for energy conservation for this type of material, assuming monochromatic waves. Now, here's the kicker. If we take the real part of that, the real part of it is the time averaged power in the volume V. So let's take the real part of that thing. If I look inside of here, is this, what's the nature of this? Real, complex, imaginary? Real. How about that? Real. I'm multiplying by a j. The whole thing's imaginary. So when I take the real part, this just goes away. Poof. And what I'm left with is the real part of that thing. So let's write it. So the integral over the surface of the real part of the complex Poynting vector, because that's the only thing that's complex.
Sorry, what you are taking the real part of Poisson?
Because the real part of that is the time average power in the volume.
By definition.
We could derive it actually, but I'm choosing not to. I'm just choosing to say what it is. Okay. So, this has to be equal to 0. So the time average power in V is 0. What does that mean? Does that mean there's no energy stored in that volume?
It means it's not generating new energy, right?
It's not generating it and it's not sinking it. Therefore, all the energy that comes into it from a propagating wave
It's coming from.
is also leaving it. And that makes sense because we've got a dielectric material and it's linear isotropic non-dispersive. Can a dielectric material suck up any energy? Can't. Can it give off any energy? No. Therefore, we would expect intuitively all energy entering must also leave. Okay, so that's kind of an obvious result. So we did all that work for an obvious result.
What about something like surface charge on dielectric material? Is that considered outside of our surface then, or?
It will integrate to 0
Okay.
over the entire surface.
Okay.
Yeah. We might have local spots of surface charge,
Okay.
but integrating over the whole thing, it's still going to be electrically neutral. Yeah. Okay, so remember why we got off on this. We're trying to figure out what is the irradiance. We want an expression with which we can calculate irradiance. That's what we want. And we've done all this work to show this result, that power entering is equal to power leaving. Now what we want to do is think about the following. What if instead of integrating over this entire surface, we just chose some region here, call it, I don't know, A naught. So that area, we just want to know how much power is going through that area. What would we do? What's that?
You would integrate over the surface probably, or something, that smaller surface?
Integrate over that smaller surface. And that would tell us how much power is going through that smaller surface. So, and I'm running out of space, so I'll just write it over here. So rather than integrate over the closed surface, I'd integrate over A0, the real part of the complex Poynting vector dotted into n hat dA, and that is going to be equal to the power going through that patch. Accept that?
Well, we said that power per area is irradiance. Why we don't call it irradiance?
Exactly my point. Because we've seen before that power is irradiance times dA integrated over some surface, that is going to be the power through that surface. So, just looking at those two, why don't we say then that the irradiance is the real part of the complex Poynting vector dotted into n hat.
What's the n hat?
It's the surface normal. So here there would be a surface normal coming out. And in general, that surface normal is a function of position on the surface, right? But let's not worry about that for the moment. Let's just say right here the surface happens to be planar, therefore n hat's a constant. Okay. So that is the irradiance. Now, a couple of points. What are the units of that?
Watts per centimeter squared.
Okay, so we have watts per centimeter squared. But per per centimeter squared implies some area, some surface. What surface? Yeah, it's that surface. Okay. So, so if I had, let's say I had some electromagnetic energy flowing in that direction in terms of a wave, and my surface was kind of tilted like this. Notice the direction of propagation is not the direction of the surface normal. That's why there's a dot product there. Because there's a cosine theta reduction of the irradiance that is in a surface that's perpendicular to the direction of propagation. So that dot product takes care of all that for me automatically.
Component that goes in the same direction.
Exactly. Exactly. Okay, so this automatically takes that into account. What if my surface normal was coming the other direction? What would the sign of the irradiance be?
Small.
Negative. Have you ever seen a negative irradiance in any sort of optics scenario?
I didn't see irradiance, the positive one.
Okay. Yeah, it turns out you never see negative irradiance. And so what we do is let's modify our definition to put an absolute value on that. Yeah.
I'm having a hard time seeing how that last equation limits it to a small area. You just take the Poynting vector times the dot product. So,
It's not limited to a small area. This could be a big area.
so it could be the whole volume.
Well, you mean the whole surface enclosing the volume? Yeah, in which case we have this result.
Yeah, okay.
Yeah.
Okay.
And then at each location then, this evaluates to the irradiance at that location.
Okay. And so how do you limit that equation if you just want a certain location? You'd have to do an integral. You put in this.
Actually,
Or
you
have
just
to-
calculate this over your surface that you're interested in.
You calculate your Poynting vector over your surface.
Well, calculate the Poynting vector, and in general, it's spatially dependent, and dot it into your surface normal for the surface of interest. Yeah.
So that or radiance equation comes from that double integral right above it?
Yeah, so we said this before, that when we calculate optical power, we can do it in terms of the irradiance through this integral. And here we just found, oh gee, through Poynting's theorem, this is the functional form of that integral. Therefore, the irradiance must be this dotted into n hat. Yeah. Okay. So when we take the absolute value here, what are we throwing away? The sign. And what does that mean?
Doesn't matter if our surface is facing toward or away from.
Yeah. Mm-hmm. We're just not worrying about whether, I mean, the surface normal, we could define, if we're not worrying about some closed volume, then our surface normal, we could, you know, if this is the surface, we could choose our surface normal this way, or we could choose it that way. Whatever. And basically, by taking the absolute value, we're just throwing away the information of whether our surface normal is in the direction of propagation or opposite to the direction of propagation. So we're not really losing anything there in most situations. Okay, so now we know how to calculate irradiance. Very good. Now what we want to do is go to elementary waves for electromagnetic fields. And yeah, let's get rid of this. And so what we want then is an electromagnetic plane wave, which it turns out has a particular name, and I'll introduce that to you in a moment. So for an electromagnetic plane wave, the complex amplitude vector I'll put in the R just to put it in there, is some constant complex vector E naught times e to the minus j k dot r. And likewise, the magnetic field complex amplitude vector will be some constant complex vector h naught e to the minus j k dot r. And e naught and h naught are just constant complex vectors. And so I could write e naught as an x component. The x component will in general be complex. So let's write that explicitly. So e naught x e to the j, call it phi x. The y component, again, is in general complex. So write it explicitly as complex. And likewise for the z component. And the vector h naught would be the same thing, but I'm not going to bother writing it down. Each component is complex in general. Okay, and then each component here satisfies the Helmholtz equation if k is the wave vector such that its magnitude is the wave number, and therefore is n omega over c, or we could write it as 2 pi over the wavelength. Okay, so then we can also go back to Faraday's law. And Faraday's law says that the curl of the real electric field is equal to minus the derivative with respect to time of the magnetic flux density. If we go back to our definitions and plug in the complex electric field vector here and here for the electric and magnetic flux density, and do a bunch of algebra, a bunch of math, we end up with the following expression, which I might have given it to you as a homework problem at one point, but I don't know. Maybe you'll see it, maybe you won't. But what this works out to be when we do all the math and cancel common factors on both sides is k crossed into E naught is equal to omega mu naught H naught. So that's what Faraday's law reduces to for the situation that we're dealing with. And likewise, Ampere's law, which is that the curl of the magnetic field is equal to the partial derivative with respect to time of the magnetic flux density. That reduces to wave vector crossed into H naught is equal to minus omega permittivity E naught. Okay, so from this expression, we learn what? We learn that H naught is orthogonal to the wave vector and the electric field vector because of the nature of the cross product. From this, we learn that E naught is orthogonal to the wave vector and the magnetic field vector. Hey, they're all mutually orthogonal. So if they're mutually orthogonal, then if the wave vector is in that direction and electric field vector is in that direction, then the magnetic field vector must be in that direction. So all of these things are mutually orthogonal. Okay. And what does the wave vector represent again? What pieces of information does it have? Direction and a magnitude, which is the wave number. So direction is what? Direction of propagation of the plane wave. So the electric field and the magnetic field are orthogonal to the direction of propagation of the plane wave. Okay. In fact, what we could do is, let's say that we had a wave propagating in the z direction. And let's say that in the x direction we had the electric field, in the y direction we had the magnetic field, and we freeze this for some time, t equals t0, then the picture of a snapshot of this electromagnetic field would be an electric field doing this. So it's doing this sort of thing. And then the magnetic field would be orthogonal to that and in phase with it. So it would be doing something like this, where this is now in the YZ plane. So frozen in time, just taking a snapshot, that's what that plane wave looks like, the electric and magnetic fields. And then if I unfreeze it in time, what happens? These things just propagate. Okay, now something else to notice is that here with the electric and magnetic fields orthogonal to the wave vector, we can call this a transverse electromagnetic wave, TEM. And so often, rather than calling it electromagnetic plane wave, often we just call it a TEM wave. But all that means is it's a plane wave, an electromagnetic plane wave. But you'll see that terminology. Okay. Now, in our last 7 minutes, we want to pull out a couple more points and make our connection back to the scalar model. Okay, so let's say that we let E naught be the magnitude of E naught, and H naught be the magnitude of H naught. And if we take the ratio of E naught over H naught, it turns out that's something that we call the impedance of the medium. So eta, the impedance of the medium. And the impedance of the medium is the impedance of free space divided by the refractive index. And the impedance of free space is the square root of the ratio of the permeability of free space divided by the permittivity of free space, which is about 377 ohms. It's kind of wild that free space has an impedance, but that's the impedance. Okay, so with that understanding, the definition, now let's go back to the complex Poynting vector. And let's figure out what the irradiance is for a Poynting vector, or rather for a plane wave, a TEM wave. And let's assume that n hat is equal to k hat. What does that mean?
Once the wave is going perpendicularly into the
into the surface that we're considering. Yeah. Okay, if we make that assumption, then one of your homework problems, you'll calculate what the irradiance is using that expression over there. And what you'll find is it's 1 over 2 times eta times magnitude squared of the complex amplitude, which is just magnitude squared of the constant complex vector E naught. Which, if we make this definition up here, I suppose we could write it as 1 over 2 times eta E naught squared. Okay, so in your homework, you'll do the calculation, and it's an easy calculation. But this then is the irradiance of an electromagnetic plane wave. Now, a couple of points. One, in most optics and photonics books, when you see them calculate irradiance, what they do is that. Is that right? No, it is absolutely wrong. So some books, they'll say up front that, hey, the irradiance is this, scaled by 1 over 2 times the impedance, and we're just not going to mention that anymore. If a book does that, then okay, technically they're correct. But in my mind, they're just being sloppy. Because I can't tell you how many people I've come across who nominally know optics who do not understand that simple fact of how to properly calculate the irradiance, at least in the electromagnetic model. But now you know, so you never make that mistake. Yeah.
So this is the irradiance of a plane wave in free space, right? So we're assuming n hat equals k hat.
No, so this is the surface normal of the surface that the plane wave is instant on.
Okay.
And we're saying the surface normal is in the direction of the
Okay, so this is
propagation.
a plane wave hitting a surface.
That's orthogonal to
Okay.
the direction it's going. Yes.
So where's an orthogonal, then we wouldn't be able to.
Yeah, then we'd have a cosine theta in there.
Okay.
Mhm. Yeah.
Would that just be a dot product then instead of a multiplication, or?
Yeah, well, we'd end up with, in fact, maybe I should give you a homework problem where you do it and you see how it works out.
I get it.
But basically what'll happen is, you know, if that's your wave vector, and we just said, hey, let's calculate the irradiance over that surface. If instead we said, hey, let's calculate the irradiance over a surface like that, then in this case, the irradiance is 1 over 2 times eta, E naught magnitude squared. In this case, the irradiance is 1 over 2 times eta, magnitude E naught squared, cosine of theta, where theta is that angle.
Hmm.
So that's how it works out. Yeah.
And my last question is, so given that the impedance of the medium is just a ratio of the electric field and the magnetic field, is that saying that there's always, never mind. I got it.
You got it? Okay. Yeah, so, and it depends on what the medium is, whether it's direct fixes. Okay, so now, final point is we want to make the connection between a scalar wave and an electromagnetic wave. So let's say that we have this situation right here. So we've got a plane wave propagating this direction. We've got a surface with a surface normal that is in the same direction as the wave vector. And what we want to know is in the scalar model, what's the irradiance here? In the electromagnetic model, what's the irradiance there? So in the scalar model, what do we do?
This right here, right?
Scalar model.
Scale it back. Oh, yeah, okay, back.
Yeah. So we basically have
Just the magnitude.
scalar model. We have that this is the magnitude squared of that thing, which if we use this notation here, would just be a squared, right? And in the electromagnetic model, we have that the irradiance is 1/2 times eta E naught squared. So we can say that for a plane wave, we must have that for the scalar model, the complex amplitude is essentially 1/√2 eta times the electric field magnitude, something like that. Now, what are the units of this irradiance? Yeah, watts per centimeter squared. So, and the electric field, what are the units? Volts per meter. Okay, so the scalar field, what are its units? It has units, but it's basically square root of watts per centimeter squared times what? Ohms, something like that. So, and you can show that if you look at this, you have volt squared, meter squared from this thing. Oh, sorry. Up here, volt squared, meter squared, and then here, this is ohms, right? So you can take this and show that it's equal to watts per meter squared. And I encourage you to go through that. It's useful to do. And so, bottom line is, this thing has funky units. But you usually don't care. Because in situations where you're applying scalar model, all you're going to do in the end is calculate the irradiance, and you know what units the irradiance is. So you're okay. Okay, well, we're out of time, so we'll end it there. Oh, and by the way, looking at this, that means you can look at the units here and the units here and show that, like if I had 10 milliwatts per centimeter squared, that would be the same as saying that I have 87 volts per meter on my electric field. So you can go back and forth easily with this relationship. Okay, well, that's it for today then. We will see you on Thursday. Yeah, we still